So we did a couple of videos the other day on NMR spectroscopy. Did video number 1 on low resolution NMR spectroscopy, did video number 2 on high resolution NMR spectroscopy, and did a few questions at the end of that. Some people have asked me if I would do a quick video on some actual CCEA past paper questions on NMR spectroscopy. So what I've done, I've just collated a file here of random NMR questions. I'll go through them here for 20 minutes or so, do as many as I can. Hopefully that'll get through to you sort of the idea of how examiners want these questions answered and how you work out structures of questions based on the information given. So let's just get started. A couple of nice simple ones in here. We've got some trickier ones. Okay, a good mix, I think. Okay, so which one of the following is, first of all, not? They very kindly put that in bold, even though some people might still miss it. Why TMS is used as a standard in nuclear NMR. So it contains 12 equivalent hydrogen atoms. That is definitely true. It is unreacted. That is definitely true. That's one of the reasons why it is used. It only produces one peak. Yep, that's definitely true. And the hydrogen atoms in TMS are not well shielded. Well, they are in fact extremely well shielded. That's why it appears so far upfield in the spectrum. Okay, let's have a look at the next one. So we've got to describe the high resolution NMR of this amide that we have here, N-substituted amide. Okay, and you need to make reference in our answer. Let's just see what we do need to make reference in our answer, provided to the integration curve. So we'll highlight that just to remind ourselves. We've got to make reference to the spin-spin splitting patterns, but they can only be labelled or on the circle groups and labelled as A and B. So we don't need to go and do the other ones. I might do them anyway, just to show you how they are done. Reference to the chemical shift should be limited to the hydrogen atoms which are directly bonded to the nitrogen. Okay, let's have a look at that. So let's go through this step by step. So first of all, we have got 1, 2, 3, those two CH3s there. So we'll call that D and we'll call that E. Those, as far as I can see, are the 4 different environments that you need to deal with here. Okay, so we've got A, B, C, D and E. Okay, let's deal with integration spectrum first of all, or integration trace, or integration curve as they have even called it here. Right, so let's deal with A first of all. We're going to have a 3, B is going to be 2, C is going to be 1, E is going to be 1, and D is going to be 6. So that's your integration curve there. Okay. Let's deal next with what have we been asked to deal with? Spin-spin splitting. Let's deal with spin-spin splitting. Okay, so if I was asked to deal with spin-spin splitting for this signal that will be produced here, it's adjacent to a CH2, so that's going to split to a triplet. Okay, in fact what I'll do, sorry, that's going to split to a triplet. B here is next to a CH3, so that on the other side of it there is a CO, so that's going to split to a quartet. My NH, which is C, NH is never split, okay, so that's going to be a singlet. My E is adjacent to my carbons adjacent to that, or this one and this one. So there are 6 carbons on the, 6 hydrogens on the adjacent carbon. So that's going to split to a septet, 7 in other words. Okay, and D, okay, is adjacent to a carbon. This is the adjacent carbon and it has 1 hydrogen, so that's going to split to a doublet. Okay. And then it asked me about chemical shift, but it only asked me about chemical shift of this particular hydrogen, which is directly bonded to nitrogen, which is a very electronegative group. Therefore, that hydrogen will be highly de-shielded and it will be very downfield. Now, I haven't got a table here with me now, but it'll be the most, so C will be the most downfield. I'm thinking probably between 10 and 12 chemical shift value. And that's your answer. If you get all that information in and you explain it reasonably well, you should get all of your marks. Which one of the following is a spin-spin splitting pattern of chloroethane. Well, let's draw out chloroethane first of all, because that would be the sensible thing to do, I think. Okay, so we have this, which is adjacent to a CH2, so that's definitely going to split to a triplet. And we have our CH2, which is adjacent to a CH3, so that's going to split to a quartet. So the answer must be triplet quartet D. Okay, compare the two spectra for chemically equivalent hydrogens. We have ethanol here and methoxymethane. Now methoxymethane is no longer on the spec, so we'll give you the structure of that. That is methoxymethane. Okay, well, if we look at this spectra here, we simply have one environment, so therefore all the hydrogens are chemically equivalent, yeah. And if we look over here at ethanol, we can see that there are three different chemically equivalent environments. Okay, and that's all the one from that particular, just looking at how many signals that there are, 3 in one and 1 in the other. Spectrum of ethanol reveals the presence of an ethyl group. Okay, so why is that? Well, if you look at ethanol, okay, it's this is the spectrum here for an ethanol, of course, it tells you down below it. And we have a quartet, so a quartet must be something that's adjacent to CH3. And we have a triplet here, so that must be adjacent to a CH2. So that tells me I have a CH3 adjacent to a CH2. We have been given a blank trace here, and we've been asked to trace what would be propanoic acids NMR. So let's go through it. We're going to have a singlet here, and that's going to be way downfield. Okay, usually about 10 to 12 for a carboxylic acid hydrogen. Here we're going to have adjacent to CH3, so that's going to be a quartet, and that quartet is going to be, it's still relatively close to these oxygens, as you can see. Okay, so and remember it's in a 1, 3 to 3 to 1 ratio. And then I have my CH3, which is adjacent to a CH2, so that's going to be a triplet. Okay, so that's in a 1 to 2 to 1 ratio. That's going to be the most shielded. Okay, so there, that's my CH3 group, that's my CH2 group. Okay, and they're definitely in the right, roughly chemical shifts. They don't have to be particularly accurate. Okay, and peak integration is also not required. So that's what they're after. Right, let's see, we have butanone. Let's draw it. Butanone, we did this quite a few times actually on the PowerPoint. Butanone, it's one that's nice and tidy and easy to do for examiners. Right, so if we have butanone, just to remind us, we're going to have 3 different environments, 1, 2, 3. They're going to have an integration of 3 to 2 to 3, and they're going to have spin-spin splitting of, that's going to be a triplet, that's going to be a quartet, and that's going to be a singlet because it's beside a carbon with no hydrogens on it. So explain why that peak is a singlet. Okay, so the peak that is a singlet is this one here. Why is it a singlet? Well, all you're really saying is that it's adjacent to CO, and there are no, I would use the word, no neighbouring hydrogen atoms. I think that's fair enough. Explain why the quartet at 2.4 has the highest value. So if we go down, this is the quartet that we're talking about here. Okay, and that quartet has got the highest value because it is the most, and I would use the word, it's most deshielded as it's adjacent to COO. You might mention that that oxygen is very deshielding because it's highly electronegative. Explain why the signal 1.0 is a triplet. Okay, so that's here, this is a triplet, and that is very simply because it's a CH3 adjacent to a a CH2. That's really the important part of the explanation there. Explain how the integration curve could be used to identify the hydrogen atoms responsible for the spectrum. Well, that would tell you that tells us quite simply how many hydrogen atoms are in each signal, or maybe each environment is I can spell environment, are in each environment. Okay. Right, here we have 2-bromopropane, so let's draw 2-bromopropane out. We have our Br here, single hydrogen there, CH3 there. Okay. So there's our 2-bromopropane. Explain the spectrum in terms of chemical shifts. Well, this hydrogen here is going to be furthest downfield, and you make a mention that it's because it's adjacent to the electronegative bromine. Okay. These are upfield because they are further away from the electronegative bromine and are more shielded, would be the word we would use. De-shielded may be the word for the one that's furthest downfield. Okay, peak integration then. If you look at peak integration, here it is in a ratio of 1 to 6, and that is because here that represents the environment here and here, so that's 2 CH3 groups together. Okay, whereas this is simply a CH group on its own. Okay, and your spin splitting, this, let me just tidy this up from here. Okay, so in this environment here, we have 1 carbon, it's adjacent to 3 on that side and 3 on that side, so therefore it has a neighbouring number of hydrogens as 6, so N plus 1 equals 7, so that's going to split to a septet, so this is split to a septet. The other environment, which I have here in the, I'll just highlight it in blue here, okay, is to those CH3 environments, and they're adjacent to this CH here, okay, and that CH is of course 1 hydrogen, so N equals 1, so that's going to split to a doublet because N plus 1 is of course 2. So it's simply adjacent to a CH. So let's just sketch propanoic acid here. So environments, we've got 1, that CH2 and that CH2 are different, and a single H there. Okay, so sketch the expected spin splitting. Well, of our OH, we're going to have a singlet. They're all singlets. This CH2 here has no hydrogens on the adjacent carbon here, but it has 2 on this side, so that's going to split to a triplet. Okay, this has got 3 hydrogens on adjacent carbon that way and 2 that way, so that's 5, so that's going to split to a sextet. Okay, so 1, 2, 3, 5, 6. I got my 2, and my CH3 here has got 2 hydrogens on the adjacent carbon. That's going to split to a triplet. Okay. How would you know using the NMR that reduction was totally complete? Well, if we started off with this molecule here, so just tidy that up. So if I looked at the molecule that we were starting off with, okay, within that molecule you're going to have a quintet here, okay, you're going to have a second singlet here, okay, and here you're also going to have a doublet. So you know when reduction is complete when those 3 peaks have gone. Okay, so you no longer have a quintet, a second singlet, and a doublet. Okay, let's look at ethyl ethanoate. So we'll just draw it out. It's always good to, I think, draw them out, guys. So ethyl ethanoate is here. Okay, what are they asking us to do? We've got to name the substance responsible for, well, that's tetramethylsilane. I would definitely name it. Don't write TMS, guys. Play it on the safe side. Explain why there are 3 other sets of peaks. Well, there are 3 other sets of peaks because, quite simply, there are 3 other different hydrogen environments. That one, and that one. Okay. Explain why the signal at 4.1 has the highest chemical shift. Well, the signal at 4.1 must be this CH2 group here, and it is some reference to the fact that it is closest to the electronegative oxygen, so it is de-shielded. Okay. Explain the term integration curve. Well, integration curve simply tells you the number of hydrogens in each environment. Okay, and use the integration curve and splitting patterns to identify the hydrogen atoms responsible for the the 3 signals. Right. So here, this is split to a quartet. Okay, so split to a 4. So it must be something adjacent to the CH3. So therefore, you would identify that as being CH2 adjacent to a CH3. Okay, so that's a CH2 adjacent to a CH3, and the integration trace on that, if you measure that, is a 2 to 3 to 3 ratio. Okay, so that just confirms it is indeed a CH2. We have here a CH3, which is a singlet. Okay, so that tells me this is this CH3 here, which is adjacent to a carbon with no hydrogens on it at all. Okay, and here I have a triplet. Okay, so that must be, and it has a peak integration of 3, so it must be a CH3. It's a triplet, it must be adjacent to a CH2, so it's that CH3 group there. Okay, which one of the following organic compounds gives rise to the largest number of peaks in the NMR? Well, let's have a quick look here. Okay, I can immediately see that this one here will give me 2. This one here will give me 2. So I'm probably thinking that that's not going to be the answer. This is a ketone here. Okay, so let me draw that out because it looks like it should give us more than 2. Okay. Well, in actual fact, when you draw it out, you will hopefully see that and that are equivalent, and the CH2s are equivalent. So that's going to give me 2 peaks as well. So let's hope it's D, otherwise we're in trouble here. Let's just draw D out. So this is D here, yeah. We're going to have a peak there. We're going to have a peak at that CH3, which is different from the original CH3, and we're going to have one here. So that one is the answer. That's going to give me 3 peaks. Okay, so here we have succinic acid. Alright, so the signal that give the name and formula of TMS, well, hopefully you're able to spell tetramethylsilane. Its formula, remember, is it has 4 methyl groups around a central silicon. Okay, use integration curve to identify and explain the hydrogen atoms responsible for 4.9 and 2.8. Well, there's 2.8 and there's 4.9. Okay, so our structure, very simply, we're only going to have this environment and that environment. Well, this one is closer to the electronegative oxygens because it's 2 carboxylic acid groups, hopefully you can see. So that's going to be the one at 4.9. It's going to be furthest downfield, whereas these ones are going to be further upfield. Okay, and if you also measure the trace, that's going to be in a 1 to 2 ratio. So you need to make reference to the fact that the ratio integration ratio at 4.9 is 1, okay, and they're furthest downfield because it's closest to the oxygens, whereas the two CH2 groups are that peak at, what's that, at 2.8. Okay, and it's at 2.8, it has a peak integration of 2, so there's twice as many hydrogens as in the other environment. Okay, and it's more upfield because it's more shielded. Explain why no spin-spin splitting occurs. Well, all the adjacent carbons have no hydrogens on them. I mean, if I just draw it out to show you, hopefully you can see it anyway. We have a CH2 with a COOH, and we have the same over here with the COOH. So OHs never split, they're always singlets. And this environment here is adjacent to that carbon or that carbon, and they have no hydrogens on them. So everything's only going to split to a singlet. Okay. Which one of the following is a spin-spin splitting of ethyl ethanoate? Well, I think we've done this one earlier, so we'll just do it again. A wee bit more practice never does any harm. Okay, so we're going to have 1, 2, 3 peaks. Yeah. This one's going to be a singlet because this carbon has no hydrogens on it. This one is going to be a quartet. Okay, a singlet and a quartet because adjacently it has 3 hydrogens, and this one's going to be a triplet because adjacent to that is CH2. It's going to be a triplet. So we're looking for singlet, quartet, triplet. So it looks like B is our answer. Okay, here we have 2 chloropropane. Again, draw it out. I think we had 2 bromopropane earlier, so this is pretty much the same question. Explain peak integration. Well, peak integration there is going to be a 1 to 6. And the reason why would we say that is we have 2 CH3 groups in one environment and 1 CH in the other environment. Explain chemical shifts. Well, our single CH, okay, here is adjacent to, make some reference to the fact that it's adjacent to the very electronegative chlorine, and it's going to be de-shielded, whereas the CH3 environments are shielded because they are furthest away from the electronegative chlorine. Spin-spin splitting at A. So A is this hydrogen here. Okay, it is adjacent to a CH3 there and a CH3 there. So N is 6, so N plus 1 will dictate its splitting. So that's a 7, that's called a septet. Okay. Why is B here? B is a doublet. Well, B is the 2 CH3s, and they are adjacent to a C with 1 hydrogen on it. So therefore it will, N will be 1, N plus 1 will be 2, so it will split to a doublet. The NMR of compound X is shown below. We've got to work it out. Okay, so let's look at the first one. We've got 1, 2, 3, 4 environments in A. So it isn't going to be A. There are 4 peaks here, but remember that peak there is TMS. Okay, let's look at the second one. The second one is an ester, and we have 1, 2, 3, 4 environments again. So it isn't going to be B. Let's look at C. C, we have 1, 2, 3 environments, so we'll draw it out just to look at it in a bit more detail. Okay. So we have 3 peaks, so it might be C. And let's look at this one. So we have 1, 2, 3. Okay. Right, so we've got 3 different environments in both of those. So let's see which one it actually is. Here we're going to have a singlet, we're going to have a quartet, and we're going to have a triplet. Here we're going to have a triplet and a quartet and a singlet. Well, that's what we have on our diagram up above as well. So that's not really helping us very much at all. Okay. Right, let's look at where the 2 singlets are. So this singlet here is a carboxylic acid singlet, and that would be very, very downfield at sort of 10 or 12. Now if we look here at where the singlet, and this actually is, it's at around 2, so that's a highly shielded singlet, or a much more shielded singlet, than you would have in a carboxylic acid. So I'm inclined to think now that this is actually C. So if we look at C, that's where our singlet would be, and it is much more shielded than this hydrogen here, which would create the singlet in the carboxylic acid. So that, it definitely belongs to C. Okay, so I'm going to leave out A. We've had that several, or A, B part I, I'm going to leave that out. We've had that several times already. Okay, we've got this time ethyl methanoate, so I'll just draw it out here. Okay, so explain the NMR spectrum of methylphenol. Let's go spin-spin splitting first of all. Okay, so this will split to a singlet, the carbon beside it has no hydrogens. This will split to a quartet, and this will split to a triplet. So the reason why this splits to a singlet, carbon adjacent, no hydrogens. The reason why this splits to a quartet, carbon adjacent, has 3 hydrogens. And the reason why this splits to a triplet is because the adjacent carbon has 2 hydrogens. Simple as that. Peak integration, this would be a 1 to 2 to 3 because we have a CH, a CH2 and a CH3. Simple as that. Chemical shift, my singlet here is furthest downfield because it's in closest proximity to these oxygens. They must be de-shielding it the most. My quartet is next closest to the electronegative oxygen, so it's de-shielded the second most, if you like. And the most shielded group is the CH3 at the end, which is shielded by this CH2 from those oxygens, so it is the furthest upfield at number 1 there, roughly. I think that's the same question we've already had. Okay, let's have a look at this. So here we have got a compound A and B. Molecular formula is as so. We have a triplet, a singlet, a quartet in the NMR. Okay, and so we've either got here a carboxylic acid or it's an ester. So we have a triplet, a singlet, and a quartet. So let's shoot for the stars, and let's go for ester. Okay, so we'll go 1. Let's put a hydrogen there. Let's put therefore that there. Let's see if this fits what we should have. So should we have a triplet? Yes, we'll have a triplet there. Should we have a singlet? Yep, we'll have a singlet there. Should we have a quartet? Yes, we'll have a quartet there. Right, so that would be one possible answer. Let's shift this about a bit and see if that helps us. Still sticking with an ester. Okay, let's have a look at this. Will we have a triplet? Yeah, that's going to be a triplet. Will we have a singlet? We're going to have a singlet down here this time. Or will we have a quartet? Yes, we will have a quartet. So it was either going to be a carboxylic acid or it was going to be an ester. So, I mean, I just want ester first. Okay. Compound C has, it only has one peak. Okay, now, I suspect what I would do here is I will have a compound called cyclohexane, which has 2 hydrogens on every single carbon in that. This is different from benzene, in that benzene has a delocalized pi system. And if you look at that, that will make C6H12, okay, and it will only have 1 singlet. Now I think you can do this another way by doing this with a CH3 here, a CH3 here, a CH3 here, and a CH3 here, and that still fits C6H12. We'll be fine. We'd only have 1 peak, so you need to be a wee bit creative for that one, guys. Okay, hopefully you get that. Compound D, molecular formula, it's a tertiary amine. Okay, so with 3 types of chemical environment. Okay, so it's a tertiary amine, so I guess the first thing that we know about it is that there's a nitrogen with 1, 2, 3 carbons coming off it. Now we've only got 5 carbons in this, so we've only got 2 more carbons to play with. Okay, and we have them in a 6 to 6 to 1 ratio. Okay, so 6 to 6 to 1. Right, okay, so let's see where that leaves us. So if I have a 6, that means I have two different equivalent CH3s. Okay, so if I make that and that equivalent, there's two CH3s there, so that's going to give me a 6. So that's one of those 6s ticked off. I've got 2 carbons left. Let's put them on. Well, okay, if I put them on there and I make that a CH3 and I make that a CH3, there's another equivalent, 2 equivalent CH3s. They'll be 6. They'll be 6. That leaves me 1 left there. Perfect. Okay. That is my 1. So that is it. That's the answer. Okay. Tricky wee one, that one, definitely. Again, guys, just an understanding that you've got to be creative. It's not a matter of just looking at that and recalling the answer. Right, I'll do another couple of these and then that'll do it. I've done most of the ones that are tricky enough. So let's have a look at here. We've got 2 chloropropanoic acid. So let's, again, I always recommend that you draw these out, guys, to make it easier for you to see what's actually going on. So we've got to do integration. So we're going to have 3 environments. We're going to have a 3, a 1, and a 1. Okay, our splitting here is going to be, this is going to split to a doublet because it's adjacent to a CH. This is going to split to a quartet, and that's going to split to a singlet. Okay, so peak 1 is 3. Okay, so it's going to split to a doublet. Peak 2 then, that's going to have an integration trace of 1, and that's going to split to a quartet, and then our singlet at the end there is like so. Okay, so here we've got propanamide or propanamide. So let's just draw it out again, guys, just to, okay. So that's propanamide. The signal at 0, explain why TMS is used as a standard. Well, it's got 12 equivalent hydrogens, which gives a very strong signal. They're all equivalent, okay, those 12 hydrogens gives just one singlet, okay, one single peak. It's inert is another reason. It doesn't react with your substance that you're actually investigating. So yeah, those are the main reasons why, or the 3 of the reasons why you'd want to use it. Explain why a signal is a triplet. Okay, so we're going to have, let's see what we've got here. We're going to have a triplet here, we're going to have a quartet here, and anything that's attached to a nitrogen, remember, is a singlet. Okay, so why do we have a triplet? Well, simply because it's adjacent. It's a CH3, it's adjacent to a CH2. So you have 2 hydrogens on the adjacent environment. Why is the signal 225 a quartet? Well, it's a quartet because it's adjacent to a CH3, it's a CH2 adjacent to a CH3. So 3 hydrogens on the adjacent environment. Explain why 5.5 is the highest chemical shift. Well, 5.5 must be the hydrogens here in blue. It's the highest chemical shift because they are de-shielded, because they're closest to or attached to the electronegative nitrogen atom. 3 ways in which the spectrum would differ from. Okay, well, let's draw the 2 molecules side by side and see if we can work out why they are different. So we're that versus okay. Okay, so 3 ways in which the spectrum would differ from the spectrum of the N-methylated compound. Right, let's look. So first of all, we're going to have 4 different signals here, because we're going to get a signal there, a signal there, a signal there, and we're going to have a signal there. Okay, so you're going to have 4 signals. The other one only had 3, so there's one difference. Okay, the next one you're going to have, let me see, splitting. We're going to have quartet, okay, and a triplet here. So you're going to have a triplet and a quartet there. Okay, we had those up above as well, so we can't quote those as being different. Okay, but here we're going to have a, oops, sorry. Here we're going to have this is going to be a singlet, sorry. Okay, and this is also going to be a singlet. So you're going to have two singlets here, okay, and you're going to have this singlet here is also going to be fairly downfield. So yeah, I mean, so, and you're going to have a different integration trace. Your integration trace is going to be 3 to 2 to 1, sorry, to 3. Okay, so you're going to have 4 signals. You're going to have different integration trace. You're going to have 2 singlets instead of 1 singlet. And I think, did I say anything else there? No, you're going to have that second singlet as well. It's going to be fairly far downfield. Okay guys, so I've done quite a few there, and I think I've had a fairly broad spectrum of questions to do with NMR. So hopefully that helps. If you do have any queries, you can come and see me in class and we can get those sorted out. But hopefully you are a bit better at answering NMR questions now. Thank you.